Hello, this is the pre-lecture video for part 2 of chapter 5. So let's begin with a couple of the problems that we didn't get to in lecture. We'll probably be starting with these in class, but I thought you might want to go through these to help us understand where we're going into the second half of the chapter. So our problem here says, calculate the heat released or absorbed when 5 grams of H2O2 decomposes at constant pressure according to the reaction. Okay, let's break down a couple things. Okay, so at constant pressure, sometimes we see this in problems, sometimes we don't. This is just meaning in an open container. That's just our reminder that delta H is equal to the heat change of the reaction at constant pressure. If it's a sealed container, it's very much related to or almost exactly the same as the heat released by the reaction. So sometimes we won't see this noted, other times we do, but it doesn't change much, or it just helps us understand that the delta H of the reaction is related to the heat change of the reaction occurring at constant pressure. Okay, so is heat released by this reaction or absorbed? Exothermic, because it's negative. That means the reaction is losing energy, it's losing enthalpy, so the reaction releases that energy. So that means energy is going to be released here. Now, if it's endothermic, then the reaction absorbs energy when it occurs. This reaction is releasing energy, so it at least helps us narrow in a couple of the answers. I think answer F is actually cut off, which is just 28.8 is absorbed. So it's possible that could be the answer too. But let's look a little bit further here. Okay, so calculate the heat released when 5 grams. 196 kilojoules will be released if we had 2 moles of H2O2 decompose, according to this reaction. If we want to calculate the heat, let's actually just try to calculate Q for the reaction actually occurring here by taking 5 grams of H2O2. Let's go to moles. So moles, it's going to be like 18.02 for water plus another 16 for the second oxygen. It's 34.02 grams. Per mole of H2O2. And the big thing here is that the minus 196 kJs is the heat of the reaction when 2 moles of H2O2 undergo this decomposition. And we're getting this 2 right from here. So the minus 196 is proportional or related to the 2 moles. Remember, if I double all the coefficients here in the reaction, I would double the magnitude of delta H. Then the delta H would be then per 4 moles of H2O2. So this ratio would be exactly intact, regardless of how many moles are here, provided the reaction's properly balanced. Okay, so then we get our Q. This is still the Q of the reaction, so it's still negative. So the Q, the heat change of the reaction, would be negative 5 divided by 34.02 divided by 2 times minus 196 is minus 19.6. What did I do wrong? So 5 divided by 34.02 divided by 2 times 196. Oh, must have just put in the calculator wrong. So it's minus 14.4 kJs. Okay, now I come back to the sign. I left it the same. I didn't change the sign. I come back to the idea that the reaction's losing 14.4 kilojoules of energy, hence it's being released into the surroundings. If this reaction is taking place, the solution's warming up because it's receiving that heat. So 14.4 kJs would be released here. 10-gram piece of iron at 100 degrees is added to 100 grams of water at 25 degrees in an isolated system. That just means the system cannot exchange heat or matter with its surroundings. So all of the heat from the iron's hotter, so the iron's going to heat up the water. Water temperature is going to go up. Iron's going to go down until they equilibrate, until they're the same temperature. Now, for any substance, we can relate a Q is equal to mCs delta T. So for the case of water's Q is going to increase in this problem. Iron here, its Q is going to decrease. Okay, so one thing we can write is that the Q of, say, the iron is equal to the negative Q of water. It doesn't matter where I put the minus sign. It just says that whatever the heat change of iron is, it's the opposite for water. And so then for iron, I can write, well, it has an MCS delta T. It has its own specific heat. And then water has its own MCS delta T. Okay, now we have to plug in the numbers here for iron on the one side and then for water on the other. Okay, so we'd be plugging in, use the provided specific heats in the textbook. We had that on a slide from the last notes, and I do believe I remember this off the top of my head, but it's 0.45 joules per gram Kelvin for iron, and it's 4.184 joules per gram Kelvin for water. So that's water, that's iron. Okay, so plug in the mass of iron, specific heat of iron, and now the TF here minus TI change is just the final minus the initial. Final is what we're going to solve for. The initial is 100 degrees. So we're going to be plugging in 10 grams and 0.45 joules per gram Kelvin. And then, of course, the change in temperature in degrees C, same as Kelvin. I don't need to worry about any conversions here because the difference in temperature in Kelvin is the same as Celsius. Hopefully you remember that from last time. Really key detail. But so then for water, it's now 100 grams of water given in the problem. The specific heat's 4.184 joules per gram Kelvin. Temperature change here, the initial temperature is 25 degrees C, 25.0 degrees C. Okay. So the key is that they have the same final temperature. So the final temperature of the water is going to be the same as the final temperature of the iron. They're going to equilibrate in temperature. So it ends up being a little bit of a either plug and chug, each of these values in, see which one works out. It can't go lower. It would make no sense for water's temperature to drop here. So water should go up in temperature so we can least narrow in. So either plug and chug in which TF works out here or just do some algebra. And I will leave it at that. I won't work through the algebra here today. Maybe we'll take a closer look at that in class next week. Okay, so the idea here of the heat changes is really what we want to do in this chapter is try to understand the heat change of a reaction. So really what we want to do is try to understand what we call calorimetry. This is our way of trying to find delta H's of reaction. So we have a reaction occurring, say, in an aqueous solution. All we really need to do is pop a thermometer in that solution, maybe have some type of stirring device so that we can stir the contents so we can get an accurate measure of the solution temperature as a function of time. And so then we look at the heat change of the reaction before and after. So you'll do this in lab, something like this. So you'll have something like the heat change before, you'll add to your reactants, and the temperature will go up, and the temperature will steady out. And so then you can do a little before or after to take your delta T, doing some propagation. Lecture example is actually a little bit easier. We don't do graphs. We don't need to worry about how to actually find delta T. It's usually just some type of given in a problem. We'll see an example here in a moment. But what we do here is you're running most of these reactions just in water, so you assume the specific heat of the solution is just that of whatever the solvent is, usually water. And you just run with relatively dilute solutions so that whatever is actually making up the solution isn't drastically changing the specific heat of the solution. So then from this, hopefully we can calculate the heat change of the reaction by looking at the heat change of water. That's the heat of the surroundings. So the big idea here, this is the most important equation in chapter 5. Heat of the surroundings is the opposite of the heat of the reaction. So if the reaction loses heat, then the surroundings gains the heat and goes up in temperature. And likewise, if the Q reaction goes up, then heat's being absorbed by the surroundings and the temperature drops. And we saw from the example in class last time that spontaneous reactions can actually occur in either one of those two scenarios. So just because the reaction needs to absorb heat doesn't necessarily mean the reaction cannot occur. Okay, so then what we do is say, how do you get to the Q reaction from the surroundings? So let's write this again, but different way. Say Q reaction is the negative Q of the surroundings, just flipping that around. Your surroundings here are just assumed to be, the solution and its specific heat. So you get the MCS delta T. So the mass of the solution, specific heat of the solution, usually just that of water, and then the temperature change of the solution. How we solve problems and approach them best explained through an example. Let's take a look at one. So here's an example. We have, the only thing I will say, these examples tend to be long in their wording, but let's take a look here. So we have calcium oxide, which is lime, reacts with water to yield calcium hydroxide. So we're told to write the balanced reaction. So that's just CaO plus H2O goes to CaOH2. Now this is a solid being added to liquid water, going to the water-soluble calcium hydroxide. And everything balances, 2 hydrogens, 2 oxygens, and a calcium. So very easy reaction to balance. So a sample of 5.40 grams of calcium oxide solid is added to 500 milliliters of water at 25 degrees C. Okay, we're given a density. I'll explain why in a minute. Assume the specific heat of the solution is equal to that of water. So we're given the specific heat of water. And then the temperature of the solution is observed to change to 27.60 degrees C. So we started at 25, we end at 27. So right off the bat, most important thing we need to know, exothermic versus endothermic, because this will probably get us a 50-50 or so percent, like we can probably narrow in on the answer here if we can get this part correct. So if the surroundings are increasing, it has to be that the reaction lost energy, lost enthalpy. Delta H here has to be negative, has to be less than 0. This has to be an exothermic reaction. Okay, so we should know that right off the bat just from the temperature change, that the solution's going up in temperature, and so that indicates heat being lost by the reaction, gained by the surroundings. So our setup, real simple. We want to solve Q reaction. We do that indirectly by measuring the temperature of the surroundings. In fact, the only thing you can put a thermometer on is the surroundings. The only thing you're really getting a measure of the temperature is what was touching the reaction before and after, and then what's the temperature change associated with that. So we get an MCS delta T. Now the only little snafu here is that the mass is the mass of the solution. So the mass of the water plus the mass of calcium oxide. So this is why we're given the density here. So the mass of water in 500 mils, we need to use the density. So 500 milliliters of water, and then multiply by 0.9970 grams per ml. ml cancels, and that works out to be just a little less than 500. So that would be 498.5 grams. Now, we're also adding to that the 5.40 grams of calcium oxide. So add the total mass, that works out to be 503.9 grams. So this is the mass of the solution. So the solution is everything here. And so then the specific heat of the solution, 4.184 joules per gram Kelvin, gram cancels. And then our delta T, final minus initial. So our delta T, let's work this out right here. So delta T, TF minus TI, in this case 2.60 degrees C. So right in 2.60 degrees C. So we do that math. And we get 5,482. So minus 5,482 joules. Now, notice again, Kelvin and degree C canceling. We don't need to do any special conversions because a 2.60 difference in temperature in degree C would equal the same difference if we converted both of those to Kelvin. So 5,482 joules. Now, this is the heat change of the reaction when just 5.40 grams of calcium oxide reacts. We want to know the enthalpy change of the reaction in kJs. The standard enthalpy of reaction assumes 1 mole of this, 1 mole of that forms 1 mole of this, not 5.40 grams. So the way we get our delta H for the full reaction is to recognize that the minus 5,482, let's write that 5.482 kJs, and just switch into kJs real quick. We're going to divide that by, that's the heat release per 5.40 grams of the reactant, calcium oxide. So we just have to write in the mass of the limiting reactant. There's only one reactant given, so that's really easy. And then we just multiply by the mass. And so that's 39.99 something. So call it 40 for calcium, 16 for oxygen. That's 56 grams of calcium oxide per mole of calcium oxide. And then this is a really easy step, but I don't want us to forget this one here. We just multiply by the 1 mole of CaO in the balance reaction. That gets rid of the mole. And if we happen to have a reaction that had 2 moles plus 2 moles of water goes to something else, then we would just be writing times 2 here, and that would change our answer. And so multiply just by the coefficient from the reaction. And then that gives us the full answer. So if we go 5.482 divided by 56, or 5.482 divided by 5.4 times 56 times 1, that works out to be 56.9, negative 56.9 kJs. Okay, so here's what we need to know. Summary here. The heat of the reaction is always the opposite the heat change of the surroundings. MCS delta T is the Q of the surroundings, and we keep our minus sign here from our relationship. And so that minus sign here, along with a positive increase in temperature, keeps the sign on our final delta H as negative. When we get the Q reaction, that's per the quantity of the reaction actually occurring in the calorimeter, and then we correct for the number of moles of reactant reacting and the moles of that compound in the balance reaction to calculate our delta H. So that's a coffee cup calorimeter example. Now, one other flavor of calorimetry is often called a constant volume form of calorimetry. We take like a bomb vessel here, seal it up. It's a closed system. Remember, a closed system is one that is a closed container, but it can exchange heat with the surroundings, but not matter. So we can exchange temperature with the surroundings, but not matter. So we have a sealed container, and it contains things like O2 gas, and then something that can combust, like a hydrocarbon. And we're going to make like CO2 and water, things like that. This reaction, and these reactions generally, and almost always, are going to be exothermic just by their very nature. So we're carrying out combustion reactions in this vessel, and then the heat changes in the temperature. So what should the temperature do in this water bath here that surrounds this bomb container that has a reaction taking place that releases heat? Well, heat's released, the bomb materials in that cell warm up, they increase, and that temperature increases in the water. So we should see a temperature increase here for these exothermic reactions generally occurring in this form of calorimetry. So our setup is very similar to coffee cup. Q surroundings is negative Q reaction. The surroundings heat is the opposite of the reaction. And I can start over again. Q reaction is just then negative Q of the surroundings. Now this problem here is usually simplified a little bit, and we'll see an example of how we solve these problems, but just into having one heat capacity term times a delta T. Back on day one in our part one in lecture, I talked about how an object, usually you define the heat capacity of an object in just units of energy per temperature. And this works when the system or the thing you're looking at is more of an object. So the object here of the calorimeter is the water inside of it, all of the parts that make it up, the surrounding materials, they all have just one heat capacity term. We multiply that by the temperature change of the solution or of the surroundings, the water bath temperature, like I said, generally should increase to work out the heat of the surroundings. Negative of that's the Q of the reaction. Best seen through an example. Let's take a look at one. So we see an example here of a bomb calorimeter problem. Oh, excuse me, before the example, one other slide. Because the volume of the calorimeter is constant, this is slightly different in terms of the way the thermodynamics works out. And so the actual calorimeter itself is measuring delta E, where delta E has that relationship to Q plus W. Work here is not going to disappear like it does for the open system, and Q is the one that's going to relate to delta H. So there is a small work change that takes place during these reactions by the very minuscule amount of pressure change that accompanies reactions that either generate or consume gas. Now, part of the reason why I mentioned in class the other day that I don't particularly like the first half of chapter 5, and the reason why is you go through all this great length to learn what work is, how to calculate and solve some problems with it. There's some numerical problems in the book that I think are mostly a waste of time because they're just phony numbers that don't mean a whole lot. What does it mean for a chemical reaction to have a work of like 20 kilojoules? The answer is it means nothing. That's a work that would be associated with a mechanical system, not a chemical system. So work is so small here that it's ignored. So like what we end up doing is just assuming that delta E is approximately equal to delta H here, and we don't even worry about this small difference in work that accompanies the reaction. confusing, but it simplifies the problem. It actually makes the problem a lot easier to solve, but it also makes the discussion of work almost like unnecessary. I'm not quite sure why the book went to great length and why we have to go to great length to understand how work can be a large quantity when for either an open system there's no work that's being done, or for a closed system there's a very small amount of work that can be done. So it just simplifies itself, very nicely in these problems, and we don't need to have too much of a discussion of what that work happens to be. Let's just look at an example. Okay, so here's the example. We have 4-gram sample of methyl hydrazine, formula given. It's a component of rocket fuel. It's combusted in a bomb calorimeter with a heat capacity given, which includes water that's insulating the bomb or surrounding the bomb. Okay, and so then we're given the balanced reaction. So the compounds reacting with oxygen to form N2 gas, CO2, and water. So upon combustion, the calorimeter goes from 25 up to 39.5 degrees. What is the enthalpy of combustion per mole of methyl hydrazine? And what is the delta H? And let's talk a bit about that in a minute in terms of what that symbol not means, of the balanced reaction above. Okay, so we're doing two things here. We want to find the enthalpy of combustion of the compound as a property, and then we also want to find the delta H of this reaction in sort of two parts. So the setup here, Q of the reaction, the heat change of this reaction, we're going to solve that from the negative of the heat change of the surroundings. The surroundings are the entire contents of the calorimeter. So we just get a C-cal times a delta T. There's no M term here, and you can see that in the heat capacity term. There's no gram unit. So all we need to do is plug in negative 7.7940 kJs per Kelvin, and then the temperature change. And so the temperature is going up by 14.500 degrees C. So the delta T is just equal to the final minus the initial. And so if I carry that arithmetic out, it would be 7.7940, the negative of that, times 14.5. That's 113 kJs. So Q reaction, 113 kJs negative. Keep that sign negative because our delta T is positive, and we keep that negative sign here. So this reaction is exothermic, as it should be, as we would predict for any combustion reaction. And so then the delta H of the reaction isn't minus 113. The delta H of just 4 grams combusting is minus 113. So we put 4 grams down below as like a ratio of the heat per gram. And then we can go and use the molar mass. So the molar mass here would be 12.01 for the 1 carbon plus 14.01 times the 2 nitrogens, and then plus 1.008 times the 3, 4, 5, 6 hydrogens. So that gives us a mass of 46.08 grams per mole of the methyl hydrazine. So grams of methyl hydrazine, molar mass of methyl hydrazine. So this would be the first number that we're looking for. So if I divide minus 113, suppose I may have lost a sig fig or two. Let me go back to my number, 7.7940 times 14.500. So that's minus 113.01 to proper number of sig figs. 5 times 5 sig figs should be 5 sig figs. Divide by 5 sig figs, keeping all 5. Maybe I'll keep my full digit 46.078 if we're being really careful. I'm not sure why it matters, but just trying to be careful here. So we're going to divide this by 4 and then multiply that number by the 46.078, the atomic weight out to as many digits as I can write it. So I get minus 1301.9 kJs per mole of methyl hydrazine. So this is the delta HC, sometimes we call it, the enthalpy of combustion of the compound. So when the compound combusts, we get 1301.9 kJs given off per mole of the compound that combusts. Now, because there's 2 moles of the compound in the balanced reaction, the enthalpy of combustion here would be 2 moles for the reaction. So we need to multiply this for the final step by 2 moles from the coefficient of methyl hydrazine in the reaction. So the delta H of the reaction is equal, so the delta H naught is sometimes just a symbol we give for the full reaction delta H. So 1309 or 1301.9 times 2 would be 2603. Keeping the minus sign, kJs. So enthalpies of reaction, usually units are just energy. The moles are assumed to be the moles of the coefficients of all the reactants in the reaction. Now the not symbol, we haven't talked too much about this. This just means supposed standard conditions. So it just means that you start with the reactants forming the products to 100% yield. And I don't want to dwell too much more on the standard conditions. There's a few more generally occurring starting at room temperature for the reaction at ordinary pressures and all that stuff. But it just means kind of your standard reaction for the full balanced written chemical reaction as the coefficients appear in that reaction. Remember, if you go back to something from part 1, if you double the coefficients of the reaction, then you double the magnitude of delta H. So doing this last step is just accounting for the stoichiometry of the given reaction. Take a look at Hess's Law. So Hess's Law is pretty straightforward. It's just the idea that if you can do reactions either sequentially or imagine them adding up together. So imagine these two reactions occurring where we have methane combusting to make CO2 and 2 waters, but in the liquid state, and then liquid condensing, liquid boiling to the gaseous state. Notice our 2 waters to 2 waters could cancel out here. So the enthalpy difference by taking these two reactions and adding them up would give us the enthalpy difference of CH4 gas plus 2O2 gas forming CO2 gas, but plus 2H2O as a gas. And all I need to do is take the reactions as they add up and take their delta H's and add them up. So if I give a little symbol 1 and 2, delta H of the new reaction would just be delta H1 plus delta H2. So Hess's Law is generally used for just taking reactions, manipulating them such that we can add them up and get a new reaction. So it's a very common problem. Maybe we give you 2, 3, 4 reactions and you have to flip them, change the coefficients, figure out the right way for them to add up to some new desired reaction, and then you adjust the delta H's accordingly. Like if you have to flip a reaction, you flip the sign. If you have to double the coefficients, you double the magnitude. And you do all that you need to do to solve the puzzle, if you will, and then just add up your delta H's of those adjusted reactions accordingly. And the reason why this is working is that the first enthalpy difference is between that and liquid water, and then the second difference is just the enthalpy difference between the 2 waters, such that the difference there is just the enthalpy difference of the original reactants and the new products where water's a gas. So it's a very simple idea of manipulating reactions to get some new delta H's. So calorimetry helps us find delta H's from experimental data. Hess's Law helps us take delta H's and manipulate them together for multiple reactions to get new reactions that maybe we can't directly study in a bomb calorimeter. So enthalpies of formation is the idea that we can define the enthalpy change of reaction for forming a compound from its constituent elements in their most standard states at room temperature. And so then if we take an example of this to be, say, propane, say the enthalpy of formation of propane, it's a gas at room temperature. It's going to come from its constituent elements, which is the graphite form of carbon is the most stable form of carbon. We need 3 of those. And then we're going to need 2 H2 molecules because H2 gas is the most stable form of hydrogen at room temperature. So we just simply take, we actually need 4 H2s to give us the right number of hydrogen. So take 3 moles of carbon solid in the form of graphite. Diamond is another form of carbon that's just a little bit higher in energy, a little bit less stable. And then H2 is the most stable form of hydrogen. Add those up to get the product. The delta H of this reaction is defined to be the enthalpy of formation of the compound. So usually they say you're forming 1 mole of the compound because the enthalpy of formation is defined to be the delta H of the reaction divided by 1 mole of the product. So the delta HF is a property in kJs per mole of the compound. Whenever you see an energy in kJs per mole, usually it's a property of something. In this case, it would be a property of C3H8. So now then the utility here will be calculating delta H's of reaction using these tabulated enthalpies of formation that you can find in something like the appendix of your textbook. So if you have the e-text, you can go to the end pages at the very end. There's a big listing about 3 pages long of a bunch of different compounds, standard enthalpies of formation. The way we can use them to solve for the delta H of reaction is just to take the sum of the products minus the sum of the reactants' enthalpy of formation values. Now the only minor confusing part here is that these enthalpies of formation are not like the absolute enthalpies. So like if we took an example being the combustion of propane. So propane combusts with oxygen to form 3 CO2, 4 waters. Let's take the liquid state of water for now, the gaseous state of O2, gaseous state of C3H8. But if we knew the absolute enthalpies of all of these molecules in this reaction, we would just take the sum of the products minus the sum of the reactants' enthalpies. So you just do the enthalpy of the products minus the enthalpy of the reactants and use that to give you the delta H, the enthalpy change of the reaction. That'd be very easy, right? And so the idea here, though, is that we're going to sub in the enthalpy of formation values. So the enthalpy takes to form the compound. So we can use it very synonymously as if it were the total absolute enthalpy of the molecule. Now, it's just really hard to measure an absolute energy or enthalpy of a compound. Much easier to measure the change of enthalpy of an ensuing reaction, like a formation reaction. So let's see this in action. Well, let's see a table of some values in action. This is just a listing of some different types of compounds and their standard enthalpies of formation. If you look in the back of your textbook, you can find these listings for a couple hundred compounds. And so then the delta HFs that are listed as 0 are going to be the most stable state for a given element. I don't see any listed here on this particular chart. But if you're not sure the elemental form of something, like say bromine, you could go to the back of the book or go to this appendix and see that bromine liquid is the one that has a listing of a delta HF of 0. That tells you that the most stable state of bromine is in the liquid state. I2 would be a solid. Turns out F2 and Cl2 are gases. So if you're not sure on some of the non-metallic elements, check the appendix. Now the 0 state for like a metal, like iron, is going to be iron solid or like sodium solid. And of course the only liquid metallic element would be mercury liquid. So these would all have delta HFs of 0. And you can double check that if you wish in the appendix. And then, so the elements are defined here to have 0 enthalpies of formation. Well, why is that? Well, imagine forming O2 gas, the most stable form of oxygen, from its constituent element, which of course would just be O2 gas. So it's just an identity reaction. So O2 gas to O2 gas. Delta H here has to be equal to 0 by definition. Now the utility here is just how we use these. Let's take a look at that. So the main utility here is if we look up the delta HF values in the back of, like say our textbook or in your end pages, at the end of the textbook using your e-text, I actually just have a print text I'm going to flip to and find the table for these values. So it's like appendix D or E. You can also find in the back of the end pages, if you haven't seen this yet, answers to some of the select homework problems. You can find answers to the figure it out, answers to the go figure questions given throughout the text, and also some of those practice exercise problems that are given within each of the chapters. Okay, so I'm just looking for the delta HF of C3H8, and I find that to be, says minus 103.85 kJs per mole. These are all in kJs per mole. O2, 0. CO2 is minus 393.5. Now for water, you want to be real careful to grab water as a liquid if you're grabbing this value from your appendix. And so if I go to water, it's under it's underneath the oxygen atom. So go to oxygen, look for H2O, minus 285.83. Now you got to be careful. Again, as I said, water gas is also listed right in the same table right above it. It's minus 242.82. Okay, so you got to make sure you grab the right value when you're looking for these. Excuse me, minus 241.82. Okay, so anyways, how do we solve this problem here? Well, if we want to find the delta H of the reaction, it's very easy. We just account for the stoichiometry. We just do 3 moles times the minus 393.5 for CO2. So just sum up all those for the products first. So do 3 moles times minus 393.5 kJs per mole, plus, because we're summing up the reactants, or summing up the products, 4 moles times minus 285.83. So we're summing up all of the delta HF values of the products. That's why this is a plus sign here. pay attention to the minus signs. Just do 3 times minus 393.5 plus 4 times minus 285.83, and then subtract the reactants enthalpies, and you just sum up the delta HFs of those. And so here, this is just going to be the 1 mole times the minus 103.85 kJs per mole. Now the moles are all canceling out. Just wanted to show that. So the moles are all canceling, so that we're left with just an energy, or delta H, in units of kJs. Exothermic reaction should be negative. I'm not going to bother solving it, but you can crunch the numbers if you want. So that's how we can use values from the appendix to calculate delta H's of reaction very easily in a problem like this. Now you might wonder, why exactly does this work? Well, think about what delta HF of C3H8 means. We wrote this earlier. C3H8 gas. Delta HF would correspond to this reaction. Let's call it carbon solid plus 4H2 gas. Okay, and so if I'm going to manipulate Hess's law right now, the delta H of this reaction would be minus 103 point whatever it was, minus 103.8, was that what it was? Minus 103.85. Okay, and then we'd have to flip this. Like, we want C3H8 plus O2 over here, and we want this CO2 over here, and we want the 4 waters as a liquid over here. And so we'd have to flip this reaction. So we'd have to have C3H8 gas going to 4C, or 3 carbons plus 4H2 gas. And then do the same thing for water. So forming water from H2 gas. Now we get a fraction here at first of O2 gas to make water liquid. The delta H of this reaction would be minus 285.83 kJs. Now we want 4 waters. We got to quadruple everything here. So we got to multiply all the coefficients and that delta H by 4. So this delta H for the C3H8, we had to flip. So delta H here would be plus 103.85. And if you do the same thing for CO2, coming from carbon solid plus O2 gas going to CO2 gas, delta H of this reaction is minus 393.5 kJs. And then we need to triple everything here to get 3 CO2s. So triple all the coefficients here, quadruple all the coefficients here, use these coefficients as they're written, and then see that everything, like the carbon solid's going to cancel, what else will cancel? The hydrogens will cancel on both sides. We have 4 hydrogens on both sides. And then what we're going to come up with is this reaction up here. We're going to come up with C3H8. The oxygens are going to add up. We're going to get the appropriate number of 5 oxygens balancing out. So we get 3 oxygens here. We get 2 oxygens here. And then that adds up to 5 O2s. And that gives us the CO2 plus the H2O liquid. So in other words, we're just tripling the delta H of CO2, quadrupling the delta HF of water, and then subtracting the delta HF of the reactant. And it just works because of Hess's law. If I confuse you here, this is just trying to show why it is that that particular approach happens to work. It just works because it's a Hess's law example. Now, bond enthalpies is the energy associated with breaking bonds. So if you want to break this bond, it's going to take energy. So bond energies are always positive. It always takes energy to break bonds. There's like a reason why the bond existed in the first place. So bond energies, or bond enthalpy, always greater than 0. There's something holding those atoms together. For CH4, you might define something like its atomization energy. Delta H here is about 1660 kJs, but there's 4 bonds being broken. So that's about 415 kJs approximately per bond. So enthalpy is always positive because energy is always required to break bonds. Energy is always released when a bond forms. from the gaseous fragments. So the idea here will be calculate the energy it takes to atomize your reactants, and calculate how much energy you get back when you make the new bonds in your products. And this will be a way that where we can approximate whether our reactions should be exothermic or endothermic based on their different types of bonds. So here's a bond enthalpy chart. We see the average bond enthalpy. So it's about closer to 413 on average for CH bond. You see some other bonds listed. So all different kinds of bond enthalpies are shown here. Okay, so don't read this here. I'm going to fix this. That's actually wrong. Look at this equation here. This is a really important equation. We can approximate as an estimation a delta H of reaction by summing up the bond enthalpies of the bonds we have to break in a reaction in the reactants and subtract the bond enthalpies of the bonds that form in the products. The way this might work is, imagine you take CH3 plus Cl2, and then we form, not CH3, CH4 methane plus Cl2, and you make CH3 plus H. So break one of those H's, and then break the Cl2. Go to Cl plus Cl. So this is going to be the bond strength of the Cl-Cl bond, however much energy that takes to break, and then we're going to break one of the CH bonds in CH4. So we're going to break one bond here, one bond here. That's going to take energy. That's a positive amount of energy. And then we can take these fragments and combine them in a different way. Let's say we take the CH3 plus H plus Cl plus Cl, and we form CH3Cl plus HCl to make some new products. Now what we can compare is the delta H of the reaction. Now it turns out this is only an estimate. This is a way of approximating a delta H because we're using, from the previous slide, the average bond enthalpies for different compounds, not the specific bond strengths within exact molecules. So this only gives us an approximation. We'll see the actual value on the next slide, but let's take a thought here of you either will have reactants up here breaking into your fragments and then recombining into products. If this is the case, then the reaction's exothermic. So this would be the exothermic reaction. Or if our bonds are less stable in the products, then the opposite happens. We'll start here, make our fragments, and then drop here. In this case here, this would be the delta H greater than 0, the case of an endothermic reaction. So this is a really useful technique for predicting whether a reaction should be exothermic or endothermic. Let's throw in some numbers and take a look at a picture on the next slide. So we see here a CH4 molecule, a Cl2 molecule. We're going to break that bond and break one of these. So we're breaking one CH bond, one Cl-Cl bond. That takes energy. That makes our fragments. And then when we make our new bonds, it ends up going exothermic when you actually plug in the bond strengths of the new CCl bond and the new HCl bond. So it turns out that the CCl bond plus the HCl bond, that these are stronger bonds than the CH bond and the Cl-Cl bond. So stronger bonds in a product leads to that exothermic reaction. This is the same case as the hydrogen reaction with O2 to make water, which we know gives off energy because we've seen it with our own eyes. So we get two waters given off here. The reason why is we start with less stable bonds, end up forming more stable bonds. So more stable bonds are stronger. So stable, stronger, leads energy to be given off when we get that greater stability in our products. So you're calculating how much energy does it take to break the bonds and how much energy do you get back when you make the new bonds. So it's the reactants minus the product's bond strengths here. When you think of your delta H here, the only thing that's a little bit weird is you're doing the initial minus the reactants, but it's just because, like we showed on the previous slide, that's the way Hess's Law works out in this particular case, because you're calculating the energy it takes to make the fragments with your bond strength with the reactants, and you're subtracting, reforming those fragments. That's why you get the minus sign for the bond strengths of the bonds that you're reforming in the products. Now notice you didn't have to break every bond. You could leave the bonds intact that don't break and change during the course of the reaction. So you can just focus on what bonds break, what bonds form. Okay, that's all for today's video. Thank you for your attention.